Hello everyone and welcome to the last talk for today. And I'm glad and proud to present my graduation project to you. My thesis was to design an energy efficient and secure system on a chip that would be able to run machine learning applications. First, let me introduce myself. I am Badawy, a computer engineering graduate from ASICs Spring 2022, and I am working as a research assistant for ASC. So today, today we'll start by introducing my colleagues who worked with me in this project, and then I will give you a motivation, then tell you about the problem that we are trying to solve, and then our solution methodology to reach the solution, and finally, what comes next. So I would like to thank all of my teammates Ashrakat Al Khalifa, Eman Asem, Mariam Musa, Nuran Abdelaziz, and Sarah Ali, and of course our supervisor Dr. Mohamed Shalan. And so let's get started. The Internet of Things or IoT is very hot and growing industry. As you can see, 8 billion IoT connected devices are utilized by 2020, and the trend is growing. Alongside with IoT, machine learning and AI are also very trending industry. As you can see, the machine learning global market is expected to increase with 44% by 2023. And imagine combining AI with IoT devices to build a smarter application to increase the operational efficiency. Also, you can see the global market of the smart IoT is expected to increase by 27% by 2026. However, machine learning models require high computational power, and if we are looking at things like image processing or speech recognition, not only that the data is constantly flow, but also the data are very large. And another challenge is the security. The communication between the IoT devices, the communication between IoT devices, we need them because the application need a frequent communication to either the cloud or other edge devices. And to secure this communication, those devices need a secure HTTPS connection. So if we want to solve the problem of computational power and space, we will train and interface the machine learning models on the cloud. However, there are some drawbacks such as transmission delay of waiting the data to be sent to the cloud and get computed there and then sent back to the edge. In addition to the high energy cost and also the security and privacy issues. So the other alternative is to move the interface of the machine learning model into the edge. That will solve the latency and energy problem and will be more reliability, but the edge is limited with resources, and we will be facing the same space and computational issues that I talked about. So here comes the TinyML into the image, which helps in optimizing and compress the machine learning models after training them in a powerful computer, and then interface the model on the microcontroller or the edge. So now we have a license flow model interface. So what we need? So we need to design a ready to fabricate system on chip or SoC with the machine learning capabilities, which meet the time constraint of the real-time application and at the same time consume the lowest power as possible. And to do so, we propose a hardware-software co-design solution in which we concurrently investigate the hardware and software component of the design and migrate some of the bottlenecks in the software level to the hardware level to reach at the end to deploy machine learning models on accelerated and secure open source SoC for IoT application. So our final product is to design a system on a chip with two extra hardware components, one for machine learning and the other for the data security. And the great news is that we reached an acceleration of 1.5x times for both accelerator, and more about the result will be later in the presentation. So let's move on the methodology used to design the accelerator. First, we choose the libraries that we will be used to interface to our accelerator. Second, we profile those libraries to identify the bottlenecks that I told you about, which are the functions that took the greatest amount of time. And finally, we migrate those functions from the software to the hardware accelerator. So starting with the security accelerator, the library that we choose is Wolf SSL, which is a lightweight C library that implements the SSL protocol, which is used in HTTPS, and this library is mainly used for embedded device. And some of its features is that it's a client and server has client and server support, and it supports lists of ciphers, and it generates keys and certificates. And moving to the second step of in our methodology to profile the library, and profiling results show that the FP Montgomery reduce function took the most time. And this function calculates the Montgomery modular multiplication, as you can see here. So, and finally, we migrate the function into hardware unit. As you can see, we obtained a pipeline design to reuse the hardware component. So we didn't consider the time constraint only, but we also consider space constraint by reusing the component. So we analyze our design using sensitive exploration feature in OpenLane to try out the available sensitive strategies against the input design. And after analyzing the best gate, best area, and best delay, and after we choose our strategy, we can see the design only consumes 7% of the gate count and almost 6% of the area of the entire SoC. And now for the machine learning accelerator. As I mentioned before, the same methodology was applied. First, we choose the NNOM library, which is a C library that deploys Keras model into a model that the microcontroller can understand. We choose this library because it supports complex structure, and it's a lightweight and has high performance and flexible interface. And okay. So by profiling the keyword spotting application for both CNN and RNN models, we found that the convolution function took almost 96% of the execution time of the NNOM library in case of CNN, and almost 60% in the case of RNN models. So by further analysis into the convolution function, we found that the MAC operation consumes almost 42%, and the memory access consumes 58% of the convolution function. So we thought of making use of the properties of convolution, such as parallelism and reusing the input data. So for instance, in that example, we have two filters that convolve with the input pixel to produce the feature output map. These two operations are actually independent and of each other, and they can happen in parallel. Also, we can reuse the input data to have a memory access just once instead of twice for each filter. And implementing that, we reached our accelerator, which has composed of 4 parallel passes, and each pass for a filter. We also analyze our accelerator same way as we did with the security accelerator, and it has a gate count of 4.7% and 3.7 area compared to the entire SoC. We also migrated the tanch and sigmoid activation function lookup tables from being in the software to the hardware in order to reduce the on-chip memory. So each tanch and sigmoid gate number is about 200, which saved the 2048 bits of being stored in the on-chip memory. So after we have done with the designing our accelerators, and in order to test them, we firstly needed to integrate them with a base SoC and then verify and validate them. So after investigating many SoCs, we choose Chameleon SoC, which is an open source SoC designed by ACADA group. You can find the GitHub link in references. And we choose that because it's mainly open source and it's available. Moreover, it has a simple architecture and the needed preference. After choosing the okay. So the verification flow was as follows. We linked a test C file with the drivers and register, and then compiled them using REST 32 tool chain to produce hex file, and this hex file we loaded into the flash through a test bench and executed it on our SoC. So after that, and for the validation, where we use CMOD RTX 7 FPGA board, and to load the program into the SoC, we added a read-only memory as slave, also as a slave on the bus, and we loaded the program into it, and we changed the load address to fetch from it instead from the flash. And by doing so, we were able to test the performance of our accelerator and get to our results. And as you can see here, our results show that there is almost 50% acceleration done by the data security engine. And by using 4 parallel filter accelerator, there are 51% acceleration in the convolution function. And now we come to the hardening part, and final part with hardening, like I said. So we used OpenLane with the Sky 130 technology to harden our SoC, and by following the flow, we get the GDS file as shown here, consuming 0.6 millimeters square with the clock frequency about 33 megahertz. And now, what's next? So if you remember, as I mentioned before, we loaded the program into the memory, but this solution has a limitation, because once the program is loaded into the SoC, we cannot erase it and load another one. So we modified our design to include a flash writer, which will be also a slave as bus, and UART master, in which we will use in order to program the flash through flash writer. And to choose between IBEX and UART master, we added a multiplexer, which will choose one master between them according to if we want to program the flash, we use the UART master, and if we want to execute our program, we will use IBEX. And in order to program the flash externally, we are developing Python script to do so, and now we are working on our script. We are able to program the flash and write the whole program into the flash memory, and now we are testing the execution part. And finally, I would like to thank all of you for your attention. I know that I give a quick description of the project because of the time limitation. So if anyone interested to know more, here is our repo for the project. You can check it. It's fully documented, and for sure, if anyone has a question here, he or she can ask to me or any of my colleagues. And thank you.